Hi there and welcome to tutorial 7, which is a lesson on graphs and in particular how you can represent graphs using matrices. This is the second in my tutorials on graph theory. It's for the EDEXCEL Decision 1 Maths A-Level course, but is applicable to most other decision or discrete maths A-Level modules. For any more help with your maths studies, GCSE or A-Level, see my YouTube channel or my website. Okay, let's start straight away by looking at the EDEXCEL specification for this. So, this is the EDEXCEL specification and it tells us we need to learn various algorithms to do with graphs, which I will do in future tutorials. However, it does say very explicitly that matrix representation for the use in Prim's algorithm is expected, and it tells us that drawing a network from a matrix and writing down a matrix associated with a network will be involved. That is to say, to draw a matrix from a network is required knowledge, in particular maybe for Prim's algorithm, and we need to go both ways round. We need to, from a graph or network, be able to draw a matrix, and conversely, from a matrix, draw the associated graph or network. Okay, let's start by looking at examples straight away. Right. Firstly, we need to know about adjacency matrices, and we need to be able to draw these matrices from the graph. What is an adjacency matrix? Well, it's simply a matrix, that's a row or array of numbers, like in a table form, that records the number of direct links between the vertices. In particular, let's look at this case here. Right. Let's take A. Between A and B, there is one direct link between these vertices. Between A and C, there's one link. Between A and E, there's in fact two links. Between E and F, there's one link. Between F and G, there's one link. Between G and D, there's one link. Between D and F, there's one link. Between C and D, there are two links. And between C and B, there is one link. Now, what about B? We're actually going to record a loop. Remember, this is a loop as two links, because we could think of it as an arc coming out that way and going into B, or coming out this way and going into B that way. So we're always going to record that as two. And also, let's say between A and G, how many links? None. Between B and E, none, etc. So we want to record this in a table or a matrix, as we call it, an adjacency matrix. First thing to do is list your vertices across as the headings of the column and list your vertices down as the headings of the row. And then we're simply going to fill in this table recording the links between each of these. Right, between A and A there are no links. Between A and B there is one. Between A and C there is one. Between A and D there is none. Between A and E there are two. Between A and F there are none. And between A and G there are none. Now, because direction is not important here, looking down this column will have the same answers as across here, because it's answering the same question. For example, how many links between E and A? Well, that's the same as how many links between A and E. So we can just fill this in directly down because direction is not important. So here it will be 0, 1, 1, 0, 2, 0, 0. Okay, let's go to B. Between B and A we know there is one. Between B and B we've called that 2. Between B and C is 1. Between B and D there's none. Between B and E there's none. Between B and F there's none. And between B and G there's none. And we can copy this down here. 1, 2, 1, 0, 0, 0, 0. 1, 2, 1, 0, 0, 0, and 0. Okay, C. We know between C and A there's 1, and between C and B there's 1, and that's recorded. Between C and D between C and C there are none. Between C and D there are 2. Between C and E there are none. C and F there is 1. Okay. between C and G, there are none. We can fill this across. 1, 1, 0, 2, 0, 1, 0, 1, 1, 0, 2, 0, 1, and 0. Okay, D. We know between D and A there are none, between D and B there are none, between D and C there are 2, between D and D there are none, between D and E there are none, between D and F there is 1, and between D and G there is 1. 0, 0, 2, 0, 0, 1, 1, 0, 0, 2, 0, 0, 1, and 1. Okay, and E, well, E is connected to A only and F. So it's 2 connected to A and it's 1 connected to F. It's not connected to anything else, so it would be 0, 0 here, and it would follow the same pattern down here, and we would have a 1 here and a 0. And F, well, we've mostly filled out F. It's not connected to A, B, but is connected to C once, is connected to D once, is connected to E once, is not connected to itself, and is connected to G. So 0, 1, and here would be a 1 here as well to have the symmetry here. And lastly, G, well, we know G was only connected to D and F, and that's already recorded. How many times is it connected to itself? None. And that is the adjacency matrix for this particular graph. And it tells us in particular, so if we were looking at it this way around and trying to interpret, if we look, say, here, it tells us that there is one link between C and F, and because everything is symmetrical in this particular matrix, i.e. symmetrical either side of this line here, we know that direction is not important. Right, you pause the video now. I would like you to have a go at drawing the adjacency matrix for this particular graph, and in 10 seconds I'll go through the answer, you mark your work. And here was my adjacency matrix for this here. I got the following. So do make sure you got the following same answer as I got there. And as in the case before, it was symmetrical about that line there because direction didn't matter. It was not a digraph. Okay, and I'd like to move on now. Let's move on to the next thing we need to talk about. It's still about adjacency matrices, but this time, can we, from one of the matrices, draw the graph from it? So here's an example here. Remember what this is telling me? Well, it's telling me that between A and C there are no links, between A and B there are 1, etc. Now let's just see if this is a symmetrical graph. 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 2, 1, 0, 0, 2, 1, and 1, 1, 1, 0, 1, 1, 1, 0. It is symmetrical about this line. That's telling me direction in the graph's not important. Now I've got 4 vertices, so the way I like to do these things is just put them in a square. The obvious shape for me is to put them in a square and then just play around with them. Okay, A and A there's none. A and B there's 1. So I'm going to draw in straight away a link between A and B. Okay? And I'm just going to, let's say, tick off as I do it. So ticked off, ticked off. Between A and C there are none. Between A and D there is 1. So I'm going to put 1 in between A and, let's say, D. Okay, between B and A there is 1, but I've already done this one. I've done these down here by the same virtue. Okay, between B and B there's none. Between B and C there's none. And between B and D there is 1, so I need to put that one in like that. And I've done these here by symmetry. Between C and A I've done, between C and B I've done, between C and C there is 2. Now the only way you can have 2 between C and D, C and C, is if you have a loop going on here. So I'm just going to draw in for us, there's a loop going on here. Okay, and between C and D there's 1. So let's draw that in. Between C and D there's 1. Okay, and I have done this one by the same virtue. And between D and D there's none. So there you go, I have drawn myself a graph from that adjacency matrix there. There are many ways of drawing that graph out, isomorphic to this, but I found it easier to draw it in a square format. Now, I'd like you to pause the video, have a go at this adjacency matrix below, see if you can draw the graph represented by that adjacency matrix. I'll go through the answer in 10 seconds. Okay, here are the answers. I would have firstly drawn out the vertices like that. Let's just fill it in together this time again. I won't go ahead. Between A and A, B and B, C and C, D and D, there are none. So I know there are no loops. Okay, and everything is still symmetrical about this here. So it's symmetrical. So I know once I've done one, I've done the other side. Between A and B, there are two. So there's one there, and let's draw another one in. Let's say as follows. Another one like that. Okay, so I've done that one. Between A and C there are none. Between A and D there is one. So let's draw that in. Between A and D there's one there. And I've done that, and I've done that, and that, and that by the same virtue. Okay, between B and C there is one. So between B and C there's one. And between B and D there's none. Okay, so I've done that one and that one and that one and that one now. And between C and D there's one, and then I've done these two. So between C and D there's one. And I've got it looking something like that. Now yours may be different. If you had the C there and the D there, for example, A, B, C, D, it would look slightly different, but it has the same, it's isomorphic to that graph. It's got the same connections, the same number of vertices, the same number of arcs. Okay, let's move on now to the next thing we need to talk about. And the next thing is distance matrices. Now what do you think these are? Well, distance matrices records the weights on the edges of the graph. It's not about connections and how many connections there are this time. It's weights on the edges, okay? So take a look at this graph here. This has got vertices A, B, C, D, and E, and it tells us various weights between these. These could be distances, prices, or anything to that effect, okay, time, etc. So I'm going to record these in a distance matrix exactly as before. I'm going to label my table as follows: A, B, C, D, E across the top, A, B, C, D, E across the bottom. But this time, one thing is, I'm labeling in weights. Now, between A and A, B and B, C and C, D and D, E and E, between A and A, there's no weight. So there will never be an answer along this diagonal here. There can't be a weight associated with just a point, okay, because there's no edge there. The weights are always associated with edges, okay. Now between A and B is 17. Between A and C there's 18. Between A and D there isn't anything. So we won't put 0, but we'll just say there's no assigned weight there. And between A and E, there's no assigned weight there. Now, there are no directions associated with this graph. It's a normal graph, it's not a digraph. So it's going to be symmetrical, just like before, okay? So if we had nothing, 17, 18, nothing, nothing, we're going to have nothing, 17, 18, nothing, nothing going down, because they just mean the same thing. Okay, from B, 17 to A, 15, nothing to B itself, 15 to C, 19 to D, and 23 to E. And we can just copy that down as well, 15, 19, and 23. Okay, and then we're going to move on to C. Well, we've done C, we've said that's 18, that's 15. C is only then connected to D, and that's 20. So 20 and not applicable, 20 and not applicable. Then D, well, we've done it connected to C and B already. We just need to talk about its connection to E, which is 16. So it's connected to E at 16, connected there to E at 16. And there we go. That is the distance matrix associated with that graph. Okay, now a digraph. This is a digraph because there's some direction here associated with some of the arcs, okay? So that's quite important to us when we're drawing out our graph. So let's do it as we did before. Label the columns, okay, R, S, T, U, V and W, and let's just fill it in. Now, R to R is not applicable. R to S is 4. R to T is 11. R to U is not applicable. R to V is not applicable. And R to W is not applicable. Okay, S. S to R is 4. S to S is not applicable. S to T is not applicable. S to U is 9. S to V not applicable. S to W is 10. Okay, from T. T to R we know is 11. T to S not applicable. T to T not applicable. T to U is 8. T to V not applicable. T to W not applicable. Okay, let's go for U here. Right, U to R not applicable. U to S is 9. U to T is 8. U to U is not applicable. U to V now. U to V is 6 because you're going from U to V, so that's 6. And U to W is not applicable. Now let's go from V. V to R not applicable. V to S not applicable. V to T not applicable. V to U. Now it's 7 this time because we're going from V to U, so it's 7. Okay, and V to V not applicable, V to W. Well, V to W is not applicable. You can't go from V to W because you can only go from W to V, so not applicable. Okay, and lastly, W. Well, W to R not applicable. W to S is 10. W to T not applicable. W to U not applicable. W to V, yes, is 9. And W to W not applicable. Now, the thing to notice, the difference between a graph and a digraph, let's just point it out clearly. A graph is symmetrical about that diagonal point, okay? It's symmetrical that everything's the same. But along the diagonal here, okay, we don't have symmetry. For example, okay, it's different from V to W, it was not applicable, than it is from W to V, okay? And that's because direction is associated with a digraph. Okay, now it's time for you to have a go at an example yourself. Pause the video, have a go. In 10 seconds, I'll go through, mark your work. Here we go. And the answers in this case here, let's just take a look now, mark your work. Here's the matrix I got associated with that graph there. Okay, last thing we've got to do, we have now got to go from a matrix, a distance matrix, to a graph and see if we can fill that in. So let's do an example, then you're going to have a go. Right. Here we've got 1, 2, 3, 4, 5, 6 nodes or vertices, so I always draw it in the shape of a hexagon. 1, 2, 3, 4, 5 and 6. And we're just going to try and fill it in from that. A to A, obviously nothing. A to B, there's no connection. A to C, there's no connection. A to D, there's no connection. A to E, there is a connection. So let's draw in A to E, okay, and A to F, there's a connection. And we know that the distances here, A to E is 15 and A to F is 8. And we know it's the same this way, okay, as well. So we've covered off all of these here. Okay, now let's go for B. B to C, there is a connection. So let's draw it in. B to D, there is a connection, so let's draw it in. B to E, there is a connection, so let's draw it in. And B to F, there is a connection, so let's draw it in. And let's draw all our numbers in there. B to C, okay, is 9. B to D is 13. B to E is 17. B to F is 11, okay? And it was symmetrical down here as well. So we've done all these. 9, 13, 17, 11, 13, 17, and 11. We're done. Okay, let's go from C. Okay, C to D, there is a connection, so let's draw it in, C to D, okay, and that's it. there's no other ones here. So C to D, and there's no others, and that was 8, and it's symmetrical, so we've done it this way. D, there was an only connection with E, so let's cross all these off, and we know that D goes to E, and it's got a distance or weight of 10, and we've done these two as well, and E and F are not connected in any way, so we can cross these off. And that is our associated graph from that matrix. Okay, it's quite easy, so you just have to be consistent in how you do it, and do watch if things are symmetrical or not, because if they're not, that will affect things. So don't just cross, just because you've done a cross, don't cross off down. Check it's symmetrical. Okay, your turn now. There's a question below. Have a go, and then I'll go through it and you can mark your work. Okay, and now it's time to mark your work. So take a look here. Here is the answer, and you make sure you mark your work against that. Okay, and that's it. That's everything we need to know about converting from a graph or network to a matrix, and then converting back from a matrix to a network or graph. Two types of matrices we need to know: adjacency matrix, which records the links between each of the vertices, and a distance matrix, which records the weights of the various arcs. Okay, then to finish with, homework and further study, you should read chapter 2, page 34 to 39, and work through the examples on those. And then you should do exercise 2B, which is on page 35 and 36, questions 7, 8, 9 and 10. Next thing I suggest you do is the past paper questions video 7, which are the questions that have come up in regard to matrices, adjacency matrices, and distance matrices, just so you practice the ones that have come up for the exam purposes. Thank you for watching this video. I hope you found it useful in your study for Decision 1.